Okay, so this is a review session. I am going for exam 1, organic chemistry 2. I will go over to your exam wrapper and some of the concepts. So the first structure we have is this structure right here. And the question is asking about the hybridization. Now what you'll want to do is you'll want to put in lone pairs, and if you remember, oxygen does 2 bonds and 2 lone pairs. Nitrogen does 3 bonds with 1 lone pair, 3 bonds with 1 lone pair. So you want to always go in there and put in your lone pairs. And the question's asking about the nitrogen. Now, to do hybridization shape, you're going to either have SP, SP2, or SP3 in organic chemistry. And so an example of an SP would be a linear carbon. And you see how carbon is bonded to 2 things. So we say, how many things? So this is connected to 2 things. And I say things so we don't look at the bonds. And so if we add the superscripts, so S and P, the superscripts equal to 2, and so that's how you can remember, and that's a linear 180 degrees. SP2, the superscripts add up to 2, and so like if you look at this carbonyl carbon here, this carbonyl carbon is connected to 3 things. And so if you add your superscripts, 1 plus 2, that's 3. And so this is a trigonal planar. You just memorize that. And that's flat. It's planar. And it's 120 degrees. And then sp3, okay, so then if you have like a carbon that's here, you'd want to put in the 2 hydrogens because carbon has 4 bonds. So 1, 2, 3, 4. And you would say, okay, there's 1 thing, 2 thing, 3 thing, and then 4 things. So that's an sp3 carbon. And so 3 plus 1 is 4 things. And then you should know that that's 109.5 degree bond angle and it's tetrahedral. So that's a review. So you do count lone pairs as a thing. So like here, this oxygen, you would say that's 1, 2, and then the carbon, that's 3 things, sp2. This nitrogen here, there's your lone pair, and you could say 1. So if you have something like this nitrogen, so what's the hybridization of that nitrogen? Well, you would count the lone pairs as a thing, and then you would have these other 3 things, so that's 4 things. So 4 things is sp3. But now this lone pair, so there's 1, and then hydrogen 2, 3, 4 is not sp3, and the reason why is because of resonance. And you have to have an sp2 or an sp2 or an sp atom to have resonance. And so if you have a lone pair that's connected to a neighbor that's sp2, it will do resonance. And if it can do resonance, then it has to be sp2 or sp, because you have to have unhybridized p orbitals. And if you remember, you have s, and then you have 3 sets of p orbitals. And when you're doing hybridization, like if you have an sp2, you've mixed these. There's your sp2, and now you have an unhybridized p orbital, and that is what you need in order for the electrons to move in a resonance. Okay, so the next question is acid-base reactions. And so we have this compound, and you need to recognize that this is your base. You can do that whenever you see sodium and potassium and lithium. That means that sodium gives up its electrons, so this is actually a hydride. And so that's your base. And then where's your acidic proton? This is an acidic proton because, so this would be your acid, and your sp carbon, hydrogen, the orbital effect, if you remember um, the ARIO from Organic 1, is a pKa of 25. This is an alkyne. That's the terminal hydrogen. So now you want to show that the hydride lone pairs go and take the acidic hydrogen, and then those electrons go back on carbon. So then the product is this, and the sodium's going to hang out with the negative, and then your hydrogen here forms a new bond with the other hydrogen, and this is gas, and this is your conjugate acid, and that pKa is, according to your chart there, 35, sometimes 35 or 40. And so the equilibrium always goes towards the higher pKa value, and in that case 35 is higher than 25. You're comparing two numbers, the acid and the conjugate acid, and so your equilibrium is going to lie to the right. All right, so the next question is making alcohols. So remember ways to make alcohols. We'll just do this as a review. When you have an alkene, you have three ways to make an alcohol, to synthesize an alcohol. If you add sulfuric acid and water, then you're going to get this carbocation, because the hydrogen from the acid is going to add to this carbon, which is a Markovnikov. You get the more stable carbocation, but this is a secondary carbocation, so you look next door and you can see that you can get a hydride shift. This is a 1,2 hydride shift. You get rearrangement, so then you end up getting your carbocation there, which is a tertiary, more stable, and then the water comes in and adds to your carbocation, and then you get an alcohol like this. Okay, so that's a tertiary alcohol. If we do what we have here, mercury acetate in water, and then we react that with sodium borohydride, then we get this intermediate with the mercurionium ion, and then we have our nucleophile, the water, the lone pairs. It's going to open from the more substituted carbon, because you get the more substituted carbon, and then that's going to give you the mercury acetate, and then the water. And you can go ahead and deprotonate that, and with sodium borohydride you could replace the mercury, and that's a secondary alcohol, and that's actually your answer for this problem. And then the other one is the anti-Mark Kovnikov, and that is your BH3. It's usually in a THF solution, tetrahydrofuran. And then you followed up with sodium hydroxide and hydrogen peroxide. This gives you the anti-Mark with this H, and the BH2 adds, where the BH2 adds to the least substituted carbon, and then when you add the hydrogen peroxide, the BH2 is replaced with the OH, and that gives you the anti-Mark alcohol. So those are three ways from Organic 1 to make alcohols. All right, our next problem is a synthesis. Okay, so you do want to know, kind of look at some of your problems, suggested problems in chapter, um, whatever the chapter is for synthesis. Okay, um, and the reason why you want to do alkyne, so you have this problem, this is an alkyne, it is a way to do homologation. So homologation is when you increase the number of carbons in the carbon chain. And so it's a very important way to do that. And what you want to do, and you'll see these types of multi-step synthesis reaction sequence um, on your multiple choice on your ACS. So this alkyne, you want to count carbons. So you say 1, 2, 3 carbons, okay? And then you see here that 1, 2, 3 came from there. And then you have these new 2 carbons that I'm highlighting in green here. So the way you need a strong base to deprotonate that hydrogen, and then you can look and you see that you have sodium amide. Okay, so that's sodium amide. That is, the nitrogen is a negative, and that is going to deprotonate that acidic proton. Remember that pKa is 25, that's your acid. This is your base. And so then when you draw your deprotonated carbon anion, carbon and anion, then you see that, NH3, that's your conjugate acid, that pKa is 35. So 35 and 25, this is happening. And so you have your sodium here. And then how do you add these two? Well, you want an SN2 reaction, so you need a primary alkyl halide with a leaving group. And so you have this, which is and then that adds the 2 carbons. So now we have 1, 2, 3, 4, 5 carbons. So you always want to do that first because you got to have this acidic proton. So that's the first step when you're doing homologation. And now what happened here? What is our functional group transformation from here to the product? We went from an alkyne to a transalkene. So this was reduction. So I'm just going to put the H in brackets. And if you remember from Organic 1, there's 3 ways to reduce alkenes. And so let's just look at all 3 ways. If we did sodium in ammonia, so metal reduction, you're going to get trans. So 1, 2, 3, 4, 5, 1, 2. So that's trans. If you do Linlar's catalyst, which is a poisoned with hydrogen, the palladium, you're going to get cis. So let's draw that. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then if you just do regular hydrogen gas on palladium and carbon, you're going to get the alkane. 1, 2, 3, 4, 5. Because it can't stop. So those 3 ways to reduce. And clearly this is trans, so you're going to want the sodium and in ammonia. All right, the next compound here, we have this reaction. And it's asking for the best reagent. And so you want to look at the functional group transformation that's happening here. So this is an ester, and you still maintain an ester. Okay, so nothing changed there. I'm just looking at the functional groups. This is a ketone, and this has gone to a secondary alcohol. So do you know any reactions that take the ketone to the secondary alcohol? This is reduction, right? And so we need a reducing reagent. We have sodium borohydride and we have lithium aluminum hydride. Okay, does it matter? Both of them will work. However, if lithium aluminum hydride will also reduce esters and carboxylic acids to the primary alcohol. Okay, so this did not reduce to a primary alcohol. The ester stayed the same. So you want sodium borohydride. All right, we have another organic transformation. And we have a benzylic primary alcohol. And we're asking for the reagent here. So you want to look at the functional group transformation. We went from the alcohol to what? An aldehyde. Okay, so we increase the number of carbon-oxygen bonds. So this is oxidation. So we need some oxidizing agents, and we have PCC, which is pyridinium chlorochromate. We also have the Jones reagent. The Jones reagent is like sulfuric acid and the dichromate. Now, this is strong, the Jones, and this is mild, the PCC. The other two options are reducing agents. And you see that to stop at the aldehyde, you need the mild oxidizing agent. Otherwise, you'll go all the way to the carboxylic acid. All right, moving on. The next reaction, you're picking the reagents again. All right, so what is the functional group transformation? Well, we went from an allylic compound, that's allylic when you see something like this, next to an sp2, allylic benzylic, okay? So that's the functional group there. And then this is allylic bromination. So if you remember, you have a few kinds of like bromine, H-nu, that, and then you've got MBS, H-nu. You also have HBr and ROR, right? And then you also just have HBr. Now these will add to the double bond, okay? So these add to the carbon-carbon double bond. They add HBr, and this is anti-Mark. It does go through the free radical mechanism. This is Markovnikov, okay? So we did not add bromine to the carbon-carbon double bond. What we did was we removed one of these hydrogens, propagation step 1. The bromine radical is going to do the hydrogen abstraction. So this is kind of like your POGL there. And then propagation step, and that's HBr. And then propagation step 2, you're going to take this same radical, and I think I redrew this wrong here, sorry. And then you're going to react that with another bromine radical, or not a bromine radical, but bromine, to give you your product. And so the best reagent for that is the NBS, which is N-bromosuccimide, because that's a low concentration of bromine radical. It's better than this. This reagent will also compete with where you add the bromine across the double bond. So if you remember that from Organic 1, that does some competition. So whenever you have a double bond present, the one you would want is the HBr, or I mean NBS. So you would want NBS. All right, so what's our functional group transformation here? We're going from a primary alcohol to an alkyl bromide. Primary alkyl bromide. Okay, so you can see that PBr3 will do that. And if you remember, you don't have to know the mechanism here, but basically phosphorus loves oxygen, sulfur loves oxygen, and so this generates this in situ nucleophile. And that's your leaving group, right? So OH is a bad leaving group, and this O phosphorus makes this a good leaving group, and so it's all going to leave, and this is your nucleophile. And if you heard me say in situ, if that's a new word for you, that means it's generated in the reaction flask. Okay, so that's what that means. It's generated upon the conversion of the OH to the O-phosphorus bond. Thionyl chloride, SOCl2, would have made this compound. Br2 is not going to do anything, and neither will sodium bromide. Now, also, let me just make a note that when you have reagents and organic transformations like this in your multiple choice, and you're starting to work your open response, you can come back here and look at some of these reagents, and it'll help kind of give you a kind of a word bank, reagent bank. All right, the next one is an epoxide. And H3O plus and methanol, and it's asking for the major organic product. So hopefully from your reactions and your POGL, you know that the first thing this is going to do is protonate the epoxide oxygen. Notice that this isn't split up as 1 and 2, so that means if there's no 1 and 2, that means it's added together. So the protonation will happen first. That gives it an acidic environment. The pH of this is probably 2 or 3. And then this oxonium ion will direct the nucleophile, which is your methanol, to this carbon. And then we have to do the epoxide opening. Now, folks, make sure that you understand that this oxygen here is this carbon here, and that goes OH, and then this oxygen that's bonded with this is going to go here, OCH3, and then the H gets deprotonated. So this opens up. Make sure you count your carbons. You see you have 6, 7, 8 carbons here. Okay, you have 6, 7, 8 carbons here, and then you have 6, 7, 8 carbons plus the carbon that's attached to make the ether and the primary alcohol. So now I'm looking for a primary alcohol and an ether, and I see the answer is B. All right, this is bond dissociation energy. You might want to work some of your problems in your book, and you might want to look through your textbook and see if you can assign numbers to these different, for these different hydrogens, these different types of hydrogens. I think you could see that this is, you do have a table in your book, and that is, I don't know, I want to say that's like greater than 400 kilojoules per mole. I think this one is the same thing because those are sp2 carbon hydrogens. This one is benzylic. I think we talked about that. That might be like 361 kilojoules per mole. And I think that this one is, it might be more than 500 kilojoules per mole. So I would look and assign numbers just to get an idea. Bond association energy, this is not acidic, okay? This is not acidic. This is a home, because acidic, okay, so when you have something like an acid, HCl, what's happening for the hydrogen with the acid is you get a thing called heterolytic cleavage. Heterolytic cleavage. So the Cl is taking the electrons, and then that generates this H proton. And so you've seen like acid is H plus. This is homolytic cleavage. Homolytic cleavage. And where you see this is the bond association energy, and you're going to have a free radical like bromine, and it does a homolytic cleavage. So it's going to take hydrogen abstraction here, and it's going to abstract the HB that has the lowest bond association energy. And so that is measured by homolytic cleavage, where these electrons split equally. So when that does that. All right. All right, so on the next problem, we've got an epoxide opening again. And this time we have a Grignard. And this is an ether, because you like to keep Grignards in ether. Notice that this time you follow it up with a 2 with the acid and the water. So we don't look at that. We treat that as separate. What is going on here is this carbon is bonded to the magnesium bromide, and this is so polar that this might as well be a full positive, and that's a full negative. So you have a negative carbon here, and that's why I'm like, you could always do this. I don't care about the bromide. We care about the carbon. And so then it's this carbon, and this is very basic. If you don't believe me, do the conjugate acid of CH4. See the CH3? What's the conjugate acid of that? That's a pKa of about 50. Okay, so this is very, 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 very strong base. Okay, so Grignards are very basic, very strong base, and that means that these electrons will open the epoxide from the least hindered side. And so when that happens, you get, keep in mind here, that this carbon is going to open up there, and then this carbon is going to form the new bond with the CH3. And you can draw the CH3 in like that. And then it is this, this will get protonated by the acid, and you will make the alcohol. And what kind of alcohol do you make? You make a secondary alcohol. And then you might want to count your carbons: 6, 7, 8, 9. 6, 7, 8, 9. Okay? So that's a secondary alcohol. And when you go to look for your options, you see that the option is A. Okay, what's the most stable intermediate in the reaction below? Well, you need to do your reaction mechanism, and then you need to look for the answers. I don't even look for it yet. Okay, so hopefully you recognize that the initiation here, the CH3, oxygen, oxygen, CH3, this splits open, gives you CH3, and then that CH3O gives you HBr, and then this splits that bond, and now you get the Br radical. You can just start with the Br radical. You don't have to, and then you're going to do the P1 though. Now you want the bromine radical, and then you got to come up here and get your starting material. Now this is HBr, so this is going to add anti-mark, and it's going to add H and Br to the carbon-carbon double bond. So when you do that, you're going to add this to the carbon-carbon double bond, and I want to add the bromine to this carbon. And the reason why is I want to get my more stable free radical. So when I do that, these electrons here, one goes there, and the other one goes to form a bond with the bromine. So you got here, and you could have these two, let's say 2 electrons here. There's one formed there, the other formed here to make that bond. So that's a bond. And so this is the tertiary radical, follows the same stability pattern as the carbocations. And now for P2, you just copy this bromine radical down, and you react it with another HBr, okay? So you react that with another HBr, and now this is the time when you get to add your hydrogen. So, and that's how you get the anti-mark, where the bromine adds to the least substituted carbon. And when you look at that, you can see that A matches this tertiary free radical. Okay, which reaction sequence would accomplish the next transformation? Let's see what we have here. This is actually a mistake, folks. So a correction in your starting material. So go ahead and, well, I can't do it now. So I'm going to scratch this out, and I'm going to do this. All right, so let's do that in your correction of the starting material. And so what you have here, you have an epoxide. What I want you to do is, when you have something like this and you have to make an epoxide, because this is a reaction sequence, kind of like a synthesis, where do the epoxides come from? They come from the alkene. Okay, so keep your carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And you all remember that that reagent is MCPBA, right? The metachloropurbenzoic acid. So then you have to figure out, how do I get from the alkene, from the alkyl halide to an alkene? And now you need to be thinking E2, and you see that this is the more substituted, so you can just use a Zatsev's base. So you just need a strong base, not a Hoffman base. And this base will basically come here, deprotonate that hydrogen, and that's how you get your alkene, and then MCPBA. So when you see that, you can see that B is your option. All right, your next one. This is to check to see, do you know how to draw curved arrows? So this is actually, so let's draw this in. It's Lewis structure. Remember Lewis structures? So just because you're giving these problems and you don't have lone pairs and your formal charges drawn, doesn't mean that you can't do that. You might need to do that to solve the problem. If you remember in Gen Chem, you would give a problem and then you'd have to do the math and add different units and stuff like that. So in organic chemistry, the way to solve these drawing Lewis structures out, okay? So something like this, you can see the lone pairs. This is your nucleophile. Nucleophiles, strong nucleophiles have negative charges. They have lone pairs. This is your electrophile. Why is it an electrophile? Because there's your positive carbon. And this is an SN2 reaction. This is actually the Williamson ether synthesis. And you can see that the other ones do not show nucleophile to electrophile. So you always want to do that when you're drawing your curved arrows. Okay, so this one you want to figure out what your starting material is. And so you have Cl and H nu. So you know this is going to be free radical. You know that this is going to give you the free radical. And in this case, you can see that that is going to do P1, and the chlorine radical will react with the starting material, and it's going to abstract a hydrogen. Okay, so remember that they abstract the hydrogen. In this case, this would be an allylic hydrogen, so that would have the lowest bond dissociation energy, and the answer would be, so you draw that, you draw in your hydrogen, you show the abstraction, and there's your free radical, and then you get HCl, and D would be your answer. All right, so now we're in open responses. You just want, if you need to do some Lewis structures, and you feel like you need some review on that. These are condensed formulas. You can always look at my POGIL 1. You all have the POGIL book. You can work POGIL 1. But basically, when you have CO, that's the carbonyl. You have the CH. Okay, so you see the negative charge. So there's that with its lone pairs. And then when you see CO2, that is an ester, and then CH3. Okay, so that's condensed formula into this Lewis structure, and then resonance structures would be like this, and then you do two curved arrows. There's also a POGIL 2 exercise that reviews resonance structures on that. And then of course we have this structure here, and once again I want to see, can you draw your correct Lewis structures, because folks, that is how you solve problems in organic chemistry, when you have to do problem solving. And so if you need to go back and refresh on how to draw Lewis structures, I would recommend you spend a little bit of time on your POGIL 1 and 2 exercises. All right, so the next one, we've already done this mechanism, and you can see that we covered that with the HBr. And so on a multiple choice question, so I'm going to bypass that for time purposes. Okay, so the next one, I feel like you can look at those answers and see, we've already done, so I'm looking at 18 and 19, we've already done those. Those are just reagents, so I'm not going to go through each one of the reaction boxes. You will get 10 reaction boxes on your exam, and then you will also have 15 multiple choice questions. You will have a synthesis, like a retrosynthesis, so you'll want to try that. So on your actual exam, You're going to have 15 multiple choice questions. You will have a retro synthesis, and you will have 20 points from 10 reaction boxes. So you'll have to either fill in starting material, reagents, or products. And you can just kind of use your test to work for that. And then I think you're going to have maybe 2 mechanism questions. And then you might have some fill in the boxes for your synthesis. Those will, and I basically went through your suggested problems to find some of these. I literally screenshot and manipulate because I don't even have a ChemDraw program um, since I'm a visiting professor. So that's why you might see on the tests sometimes the formats and the structures look a little different and look a little funny. And that's because I'm having to use free software and learn how to use the free software. And anyway, not important in your world. What's important in your world is that you know that 50% of your points are coming from those suggested problems. So try to take some time to work those in your textbook and look at your textbook. And I will see you on the exam day. Be test ready, okay, folks? And I'll see you soon.